All right, hello everyone. This week we're going to get started on our first bit of real lecture content for this semester, starting off with chapter 16, talking about conjugated pi systems, and then going into a certain class of reactions called pericyclic reactions. Before I dive into the content, one thing I want to say about sort of the design of the course that I think is really important. As you see opening up your Canvas page, things are organized such that there's a lecture and then there's an activity, and then there's a lecture and then there's an activity. It's really important that you go through in this particular order that's been set, because a lot of these concepts are just going to build off of the previous concept. So you can't skip ahead to something because you just won't have the context yet. The other thing that I want to stress is to make sure that you're not like going through and watching the videos and saving all the assignments till later. It's really important that you do the assignment right after you watch that lecture video. This is the one way that we've really been able to improve upon what would be like an in-person organic chemistry course, is that instead of having to listen to me talk for an hour and 20 minutes straight and then being expected to retain all that, you can kind of get this information in little bite-sized chunks, and then forcing you to practice right afterwards will just help it set into your long-term memory bank that much easier, right? So it's a much better way to learn, breaking these things up and having that little bit of practice right afterwards. Okay, so how we're going to start, we're just going to start by introducing this idea of conjugated dienes. So let's pick this apart real quick. Dienes, right? So these are alkenes with two double bonds, right? So hopefully by practicing that nomenclature again, you remember what a diene would be, hexadiene, something like that. And we'll talk about what exactly it means to be conjugated in a second. First, let's talk about the nature of pi bonds in general, right? So alkenes, of course, they have double bonds. If you have a double bond, that's one sigma bond and one pi bond. The pi bond is really what's special, okay? Because the pi bond takes place between overlapping p orbitals, right? So what I would be drawing in here, this would be a pi bond that's occurring between the p orbitals on these sp2 hybridized carbons here. This would be ethene, or if I were to just draw it out, CH2. Double bonded to CH2. That's what's being depicted here. The red and blue that you see, those are those p orbitals. And so that second bond that's formed is an overlap between those p orbitals, and that's what we call a pi bond. Pi bonds are special, as we're going to see here, in large part because of this geometry where they stick out perpendicular to the sigma bonds in a compound. All right, types of dienes. By far the most rare would be the cumulated diene. So this is when you have your two double bonds located directly next to each other. This is an sp hybridized carbon in the middle there, okay? The special, super duper special one that we're going to spend a ton of time talking about in this chapter is a conjugated diene. Okay, so we have our two double bonds, but then importantly, there is exactly one sigma bond between them. What's really important about a conjugated diene is the fact that you have this line of sp2 hybridized carbons. Okay, we'll see why that is in a second, but that's one of these things that makes a conjugated diene special. And again, you can spot them because there will be exactly one sigma bond between the double bonds. An isolated diene is anything that has two double bonds, but there's three hybridized carbon. There's something interrupting that sort of conjugated network. So they're not all sitting all in a row. There's one or more sp3 hybridized carbons that's going to mess up that conjugation. So it doesn't just have to be one. Something like this would also be an isolated diene. Anytime you have that network of sp2 carbons that are all lined up next to each other broken, it's no longer a conjugated diene, it's an isolated diene. And again, this is the special one. So why is that? Well, so now we're going to look at this sort of atomic orbital is a lobe sort of picture of things here. If it's accumulated diene, that means that this guy in the middle is sp hybridized. You can go back to chapter 1 if you're a little bit confused about this hybridization stuff. We reviewed that, but nonetheless, for accumulated diene, those two sets of pi bonds actually sit perpendicular to one another. Okay, one set is pointed perpendicular to this plane that's drawn. The other set is pointed parallel to this plane that's drawn. Okay, what that means is that those p orbitals can't really talk to one another. They're kinked out of the plane. Conjugated diene, what makes a conjugated diene so special, remember I said you have to have this line of sp2, 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 which means that there are p orbitals sticking up all in a row next to each other. And so what we're going to see is this makes it so that these electrons can freely travel throughout this whole network of pi bonds. So instead of being just isolated between, so I guess real quick, whoop, just to be clear, this compound that's being drawn here would be 1,3-butadiene, okay? Where when we draw it in our sort of stick figure fashion here, we of course see that we have 1, 2 pi bonds. But when we draw it with these cartoons of the p orbitals, we can see that these pi bonds can kind of bleed into one another or conjugate. That's what we mean by conjugation. Is an electron's ability to sort of travel freely through that network of p orbitals. So then all of a sudden when we interrupt things with this sp3, so this would be, for example, this guy here, and again, we know that this is isolated because we have this carbon here. The reason why I say it messes up that conjugation is because it does not have a p orbital that it's able to contribute to this network. So there's no way for this double bond over here to communicate with this pi bond over here. But when they're all in a row, and again, you can see that because there's this one single bond separating them, or again, another way is they're all sp2 carbons all lined up in a row. These pi bonds can like talk to each other, okay? The electrons in these pi bonds are free to diffuse across that whole network. They don't have to be just alkenes. You can have heteroatoms that are involved as well. So here we have, again, this would be called an enone. We'll talk about that more when we get to ketones. Ene for the double bond, one for the fact that there's this ketone or this carbonyl group. Anyway, point being, again, we have pi bond here, separated by a single sigma bond. And importantly, everything is nice and sp2 hybridized. So again, just like we saw before, there are a bunch of p orbitals sticking up all in a row where those electrons can diffuse. Likewise, down here, we have this heteroatom as well. Of course, these pi bonds are all in conjugation with one another because they're all spaced nicely apart. But in addition, this one over here can also talk to that network, right? Again, everything in this position, all of these guys have a p orbital that's sticking up, all lying in this same plane, and these electrons can kind of freely pass through that network. This guy over here, though, is not. This is going to be an isolated pi bond. He's over there. He can't talk to anybody else because they have these sp3 hybridized atoms messing up that conjugation. Okay, so skill number 1 that's going to be important is being able to spot conjugated dienes as well as the cumulated and isolated, right? So being able to classify. The one thing I will say is the chapter is dienes. We are going to be focusing mainly on dienes. Conjugation is true for trienes, tetraenes. I mean, as long as you have that perfect spacing of pi bonds, it could be as long as you can imagine. But we are going to focus mostly on pi bond or on dienes. One of the physical observations is that the more conjugation you have, so I guess this would be a good example of a conjugated triene and a conjugated tetraene. The more highly conjugated your pi network is, the smaller the energy gap between what's called the HOMO, or the highest occupied molecular orbital, and the LUMO, which is the empty, lowest unoccupied molecular orbital. Remember that in spectroscopy, what happens is we have, oh, that's terrible. I'm not an artist, bear with me. We got a light bulb of sorts, and it is firing a whole bunch of wavelengths of light into our sample. And then we're going to measure what actually comes out against our detector. Okay. Pi bonds will absorb photons in the visible light spectrum, or UV spectrum. These are all sort of 270, 250, 290. Those are all on the UV spectrum. The more conjugated pi bonds you have, the longer the wavelength of light that will be absorbed, or consequently, the shorter the energy gap is between the HOMO and the LUMO. Why this is really consequential is, first of all, it's a good way to measure stuff, right? It's easy to send light into a sample and measure how much comes out. Another reason is a lot of the brightly colored, in fact, all the brightly colored compounds that you see around you, the dyes, everything like that, they're brightly colored because they have large networks of conjugated pi bonds. Okay, so if you think of something, some brilliant yellow fabric dye or something like that, I can guarantee that that dye molecule has this huge network of conjugated pi bonds. Moral of the story, though, is more conjugation equals longer absorption wavelength, right? So these are going to be measured in nanometers. Those units should be there. And we'll talk a little bit more about the MO picture of pi bonds in a separate lecture. I've kind of put that off to the side to talk about all by itself. But this is the take home that I want you to know for this lecture. All right, now talking about bond length. So we learned way long ago that a double bond is going to be smaller than a single bond, right? There's more electrons being shared. They're also stronger. They require more energy to break. However, it's also true that a single bond in a conjugated pi system is actually shorter than a single bond in just a regular old alkane. The reason is because it takes place between two sp2 hybridized carbons, right? Again, the whole thing about conjugation is you have this network of sp2 hybridized carbons. So an sp2 carbon single bond is shorter than an sp3 carbon single bond. So why is that? So remember, this is where you got to sort of rewind yourself back to chapter 1, and when we talked about hybridization. So these are hybridized orbitals. Remember that you have atomic orbitals like this guy and this guy, an s orbital and a p orbital. That's what an atom is made up of when it's all by itself. But when you start to bring it in contact with another atom and it forms bonds, those orbitals will hybridize. sp3 orbital is one s orbital mixing with 3 p orbitals. So we say it has a quarter s character, 25% s character, versus an sp2 hybridized hybrid orbital, which has 33% p orbital. The real sort of takeaway here is just look at the sizes of these, right? The more s character you have, the shorter those hybridized lobes are, right? So this guy here is just longer than the sp2. And going even further, we can see that if we had a single bond made up between two sp hybridized atoms, so something like this bond here would be even shorter than with a conjugated diene. Okay, again, those you can see the sort of length of those hybridized orbitals that are making up those sigma bonds. Okay, something we talked about in chapter 7 when we introduced alkenes. This is sort of when we were talking about elimination reactions. We'll talk a little bit more about that in a second, is just alkene stability. Okay, one of the things that we found is that the more alkyl groups, the more highly substituted an alkene is, the more stable that alkene is. So what do I mean by that? So first of all, notice that my little gradient here is in terms of increasing stability. So what's the difference between these? Well, so this alkene here has 1 alkyl group and 3 hydrogens. That's less stable than if it was disubstituted with 2 alkyl groups and 2 hydrogens. Less stable than if it was 3 alkyl groups and 1 hydrogen. And the most stable is if all of those, you know, for example, methyl groups or something like that, all of those substituents on that alkene are alkyl groups, right? That would make that alkene more stable. So more highly substituted means more stable. Now, that was true for regular old alkenes, not even talking about dienes or conjugated dienes or anything like that, okay? This idea that more substitution equals more stability. Now, specific to conjugated dienes is this added extra energy that you get from having a conjugated set of bonds, okay? So for example, let's take 2 isolated pi bonds, right? So as in this compound here, and if we were to hydrogenate them, basically reduce them all the way to an alkane rather, it would release a certain amount of heat. Well, if instead, and there's 2 of them, right? So I'm hydrolyzing, not hydrolyzing, that's not, hydrogenating or reducing 2 double bonds. The difference is that they're isolated. Now, if I do the same thing, I reduce 2 double bonds, but here they're conjugated, that releases less heat, which means that this compound here was lower in energy than 2 of those molecules there. The bottom line is that there's an added stability to having conjugated pi bonds. Like we're saying, those electrons can go across that network of pi bonds. They want to spread out as much as possible. That's a low energy state. So by having conjugated pi bonds, you add this extra benefit of stability. Another, I think maybe a better example, instead of using these, would be if I took, for example, do this compound here. This would be 1, 2, 3, 4, 1, 4 pentadiene versus 1, 3 pentadiene. Both of those would reduce to pentane. The same number of carbons, same number of hydrogens. The only difference is that this is isolated, an isolated diene, and this is conjugated. And you would see the exact same thing, that the isolated 1,4-pentadiene would release more heat than the 1,3 conjugated pentadiene because of that conjugation, because of the added stability that you get from having conjugated double bonds. Okay, so then in terms of evaluating the stability of a compound, this would be a good thing for you guys to pause and try to do for yourself. The first thing you want to do is figure out which one of these pi bonds are conjugated and which one are isolated. Okay, so I'm going to go through, let's do red for isolated, and we'll do blue, oops, for conjugated. Okay, so for A, all of those bonds are isolated. They're all too far apart. There's sp3 hybridized carbons. For B, we see that this one's isolated. I'll actually make this smaller. For C, again, we can see that this one's isolated. And then for D, there are actually no isolated bonds, right? We have the 1, 2, back to the double bond again, boom, boom. So these all 3 are conjugated together. In C, we have these 2 conjugated, and B, we have these 2. So right off the bat, we can say that this is the highest energy, or the least stable. This is the lowest energy, or the most stable. So now what about B and C? What differentiates them? They both have one isolated, I'm gonna sort of clean things up here and zoom in. One isolated and two conjugated. I'll color code again, but let me clean it up. Okay. So now which one's going to be more stable than the other one? This is now now that we have a tie, two conjugated, one isolated. Now we have to go back to this idea here. The idea that more substitution leads to more stability. So which one of these has the more highly substituted of the pi bonds compared to the other one? So you can just sort of go through and count. This one has 1, 2, 3, 4. So we'll make a note next to it. This one has 1, 2, 3. This one has 4. So now focusing on this one here, it's got 1, 2, 3 alkyl groups. And then we go up to our isolated double bond and it has 1, 2. Okay. Now moving over here, we have for this isolated double bond, 1, 2. Okay. What about this guy? Again, 1, 2. And finally, 1, 2, 3 for this one here. So that would be a 3. So now you can see that B is going to be the next lowest energy because it has the more highly substituted double bonds. So in terms of ranking them, this is the highest, this is the lowest. Oops. This will be 2 and this will be 3 in terms of high to low energy. Okay, I think, no, almost. Preparation of these conjugated dienes. Okay, so remember when we were talking about elimination reactions, so this would be back to chapter 7 if you guys need some review, elimination. One of the things that you are going to find when you're going back and reviewing is, right, we spent 18 weeks on that stuff. So you're not going to learn it all in a day, okay? You need to make sure to focus on the big picture stuff at this point, right? So being able to understand which substrates combine with which reagents to give which products is really important. The mechanisms, the stereospecificity, that's all well and good if you can remember it, but most importantly is just kind of the which substrates combine with which reagents to give which products, which is really easy to flashcard. So if you're finding yourself, I know that there's a bunch of students out there who have taken the first semester, not just last fall, but a year ago or something like that. Bust out some flashcards and start reviewing those combinations of substrate, reagents, and products, okay? One of the things that you'll find is that this is tert butoxide, okay? So if we wanted to draw out what this looked like, it's what we call a big bulky base. It's got these methyl groups sitting over here. It's a very strong base. It's basically just a deprotonated alcohol. So it's very strong base, very good at removing hydrogens, but because it's so big and bulky, it will remove the hydrogen from the least crowded environment that it can find. So instead of removing from the more highly substituted carbons, it removes from the less highly substituted. I guess one sort of simple example to give real quick would be, let's not talk about dienes for a second. Let's just talk about alkyl halides. If we had a small base, something just like hydroxide, OH minus, we would expect it to pull from the more highly substituted carbon and give us that more stable alkene. But if we use tert butoxide, it will actually pull from the less highly substituted carbon and give us that terminal alkene. Okay, so that's just sort of review from chapter 7. So now let's talk about our conjugated dienes here. Again, the goal is to form conjugated dienes. We can do so with tert butoxide. okay? If you start off with something like this, that's well and good, but even more common would be to start with something like this, because this is easily formed by taking an alkene and adding Br2. Now we can get to this dihalide. And if we treat with terbutoxide, it's going to remove the carbon, the hydrogens from those less highly substituted carbons and give us a conjugated diene. Okay, so an alkyl halide, a dihalide in the presence of terbutoxide will have a tendency to generate dienes. It does not form, notice that it will never form those cumulated dienes. Those are way high energy. The other reason why this reaction favors forming conjugated dienes is everything that we were talking about stability. They're way lower energy than isolated or cumulated dienes. So in that sense, they're also more favorable. All right, so last, right? Yeah, so last thing we're gonna discuss is the rotational conformations of a conjugated diene. In particular, we're going to look at butadiene, right? And I guess, well, yeah, you could. So in particular, 1,3-butadiene. So something like this. When we draw our molecules, we almost always do them in this elongated fashion, right? Remember about double bonds. Double bonds cannot rotate about their double bonds. You can't rotate about a pi bond, but you can rotate about this sigma bond here. So there are two rotational conformations for butadiene. One of them is called S-trans. That would be the one that we're sort of used to seeing all elongated. Notice the S, it's like a kind of trans, right? So it's not the same thing as a trans in our normal sense, because we're not talking about substituents that are on, all right, so. This would be our traditional trans when we're talking about relationship to a double bond. We're talking about S-trans, we're talking about where those double bonds are relative to one another. But they can also, this molecule can also rotate about that single bond and a sigma bond, but single bond in order to form this S-cis conformation. Okay, this is, well, these are the two most important ones, because in both of these, the pi bonds are still conjugated, right? In the S-cis, you can see that they're still nice and neat in this network. Same with the trans. The most important thing for conjugation is all those p orbitals lined up right next to each other, okay? However, the S-cis is higher in energy than the S-trans, right? That's because there are these hydrogens sticking off the end here. So you just have some steric clashing that occurs in that S-cis conformation versus the S-trans. This would be way, way worse if, for example, instead of just talking about butadiene, we were talking about something that had big bulky methyl groups or something like that. That would increase the gap. That would increase the gap quite a bit in the difference between these two conformations. Okay, so steric clashing is what leads to the S-cis. We're going to see that this S-cis is really important though. So don't just dismiss it as whatever. Interestingly, and this is what we're going to talk about now, is the fact that there's this big energy hump that has to be overcome in order for this rotation to occur. Why would that be? Well, again, remember that in both of these conformations, the S-cis and the S-trans, you have conjugation. You have those p orbitals lined up next to each other. But what's going to happen when you rotate about that sigma bond? You're going to have to break that conjugation, right? So that transition state, this guy right here, is going to look something like this. That's actually a pretty terrible picture. But nonetheless, going to look something like this, where you have these two sets of p orbitals that are actually now perpendicular to one another. Right? So you have to break your conjugation to flip from one to the other. So that's why you have this pretty big energy hump that needs to be overcome for a S-cis to S-trans conversion. Okay.